Right, hello, it is me, guest lecturing this chapter. Okay, I'm going to take you through the last few subtopics in chapter 20, which is DC circuits, and also through the more confusing questions. And mostly people kind of don't really pick to circuits because, right, there are plenty of wild cards. But I love them. Come on, think about it. Not all questions are predictable, and if you can do well in them, it really means that you really understand this. In other words, circuits is a lot like a puzzle, where if let's say you have the key and you know how to apply it, you can unlock a lot of different scenarios lah. Okay, so I'm not going to talk to you about the potential divider circuit. We're going to start with level 1 first. Okay, and there are some basic ideas that we need to go through. So if you've not yet watched Miss Ellie's video about series circuit, parallel circuits, and Kirchhoff laws, I would suggest you pause this and go watch that one first, because that would probably set you up with a proper theoretical framework. And here I'm just going to talk about the main ideas and not go through the laws again. Okay, so you can see, right, whenever there's a potential divider circuit, physics people, we are very literal one, you know, like if we name things exactly the way it's supposed to function. We're not going to put in some fancy names because ain't nobody got that kind of brain or head space for that. So potential divider circuit, it's meant to divide the potential. Okay, so this happens whenever you have two resistors in parallel, like so. For example, in this particular circuit, the first one you can see there's a LDR. Okay, the LDR here is in series with another external resistor. They can put anything lah, okay? Don't worry. Alright, as long as it's a resistor, you got this. So if they are in series this way, right, resistors in series will share potential in proportion to R. Okay, so my whole idea here is you use ratio. If you've not watched my videos before, or if you've not heard me say this, listen carefully. Ratio is your best friend all the time. Okay, so when you use ratio, this here means that the ratio of VL to VR, okay, is the same as the ratio of RL to R. This means, right, the potential across the LDR is in proportion to the resistance. Well, why? Two reasons. Number one, if you're going to look at the current inside the circuit, right, the current coming out from the battery that flows through this LDR is the same current. Okay, so the first justification I can give you is from Ohm's law, V is equal to IR. Since the current passing through both resistors is the same, V is proportional to R. Okay, this means that the ratio of V will be equal to the ratio of R. Or you can look at it this way. Potential is defined as work done per unit charge. So the larger the resistance, the more work done you need, the higher the potential it will be. Right? So there's a conceptual thing, there's also a mathematical equation thing, and they have to complement each other. Okay? Like fries and tomato sauce. Alright, so next, because these two are in series, the sum of the potential will be equal to E. Okay, so if you take the potential across the LDR plus the potential across the resistor, you will get the EMF of the battery. Alright, so I'm going to do a question now with you. Okay, hi, and we will now look at this example. Abrupt cut. Okay, so here you have a fire alarm system. Thermistor T has a resistance of 2000 ohm. Okay, very good. At room temperature, so its resistance decreases as the temperature increases. Do you know why? Well, this is probably because this thermistor is made out of semiconductor. So for semiconductors, when it's being heated, you get more free electrons. More free electrons, better conductivity to carry the charge, lower resistance law. We will talk more about semiconductors in the future topics. Okay, so anyway, I'm just going to write this down in case it's relevant. Resistance decreases when temperature increases. So the alarm is triggered when the potential difference between X and Y is 4.5 volt. So this means that the potential difference here is 4.5 volt. What is the resistance of the thermistor when the alarm is triggered? Okay, so I don't know the resistance, but I definitely know the potential because these two are in series. So 12 minus 4.5 means that this is 7.5 volt. It's time to use ratio. What ratio am I talking about? The ratio across the thermistor to, the potential difference across the thermistor to the potential difference across the 150 ohm, which is equal to 7.5 out of 4.5 is equal to, let's call this RT. It's also equal to RT ratio 150. Okay, so it's a bit like if A ratio B is 1 to 3, okay, and also at the same time equivalent to 150 to X. Find X. You know what to do, right? You know what to do, right? Okay, so this is a method. What you can do is you can take RT divided by 7.5 is equal to 150 or 4.5. I'm doing this so that RT remains the numerator. I come from a background with not that great a calculator because I am that old. So there you will get RT as 250. There are many ways to solve the problem. This is one of them. Okay. Another way to solve it right would be, you can say, we are now trying to divide 12 volts between RT and 150 ohm, such that the outcome for RT is that it gets 7.5 volt. So the portion of RT out of the total portion, RT plus 150 would be 7.5. So you can find RT using this method as well. 7.5 divided by 12 is 5 over 8. This is RT over RT plus 150. Cross multiply, 8 RT would be equal to 3 RT. No, wait, what 3 RT? 5 RT plus 750. So from here, RT would be 750 divided by 3. That would be 250 ohm. This one also can. Okay. If you ask me, I don't know. I see mood one. Another method that someone else might do this. I won't do so many methods moving on. Okay, I'm just showing you. 150 ohm times 12 will give me 4.5 volt. Okay, and 150 is ratio out of the total, so RT plus 150. Okay, so 4.5 divided by 12 would be 3 over 8. See, 5 over 8 plus 3 over 8 is 1. Okay, again, depending on your mileage. If you are generally not very good with ratios, right, or you can do but you don't know what you are doing, please try to figure it out. It's worthwhile. Okay, so here I'm gonna take 8 multiplied by 150. So I'll get 1002 is 3 RT plus 450. Is it? Yep. So I will get RT as 250. Yep. 250. Do whichever you want as long as you arrive at the answer C. Okay? This is why it can get very confusing if you're looking at textbook, because they're not consistent in their method, because this one is a matter of preference. Okay? Everyone got different preference. Alright, moving on. Miss, what happened if I got more than 2 leh, like that leh? Aiyo, then your ratio level up lor. This one is A ratio B. Now let's say this is resistance RA, or never mind, R1, R2. Oi, okay, never mind. R3. I'm going to label the resistance. Okay, if you're wondering why they keep going missing, it's because there's actually a value here. Okay, so I'm going to just not bother too much. This is R2. I'm going to write on top here. This is R3. Okay, so let me see. If you want to talk about ratio, okay, I'm going to try to write over it if I can. This is R1. Okay, it's going to look very weird. Hang on. Technical issues all around. Okay, I'm just going to rub and show you the resistance. Okay, so this one here, right? Let's say this is R1. Okay, and this is R2, and this is R3. All right, we are still going to divide amongst them equally. It's a little bit like, okay, now we break apart the company, so each subsidiary will get a certain ratio of money. Okay, so the ratio here will be 4 to 3 to 2. So since R1 ratio R2 ratio R3 is 4 to 3 to 2, first one, and then so hence V1, the potential across R1, ratio V2 ratio V3 will also be equal to 4 to 3 to 2. But also at the same time, the sum of all the potential difference will be equal to the battery that is connected across it. Okay? Then you do maths law. Do maths. So example, if you want to find V1, you will take, okay, 4 portion out of 4 plus 3 plus 2 portion and multiply by 9 because you are sharing the 9 volt. So you will get 4 over 9 times 9, so you get 4 volt. No? Just so happen lah, you add together, you get 9. You get, so I think we all know this will be 4 volt, 3 volt, and 2 volt. But you look at this voltage output, this one is a jockey or a connector here, this connector here. It can be moved such that it does not include the 3 ohm, include some part of the 3 ohm, and include the entire 3 ohm. So the output voltage, right, V out, here also we write it down here, V out must be between, okay, so if let's say it's at position A, let me change color a bit. So let's say it's at position A. So at position A, V out is 2 volt, okay, only the 2 ohm resistor. And then at position B, let's say this position here, your output voltage will be 2 plus 3, which is 5 volt. So your V out, right, is actually between 2 to 5 volt. Okay, can Alright, so essentially I copy the question here. We answer a question now. Are there 2 to 5 volt? So our answer would be B. What's the maximum and minimum output voltages of this one? Ratio is your best friend. Okay, let's continue. Alright, so I'm going to run you through some questions now and solve them pretty quickly. Here you have a potential divider consisting of a LDR and a variable resistor. The resistance of the LDR decreases when the light intensity increases. So all these they tend to tell you during the exam. But LDR is also a semiconductor. So if you shine light on it, the electrons get more excited, they are more mobile, then the resistance will decrease. Okay? So the variable resistor can be set to either high or low, which situation gives the largest output voltage. Okay, sure. So if you want the largest output voltage, right, you would first and foremost want R to be as large as possible. So this one is out, this is out, okay? Number two, you want the resistance of LDR to be as small as possible, so it doesn't steal the 10 volt away from you, because you are sharing with 10 volt in proportion to the resistance. As R, variable resistor, I want the most share possible. So my partner, my neighbor, the LDR should have a very low resistor. Low resistance means low resistance. So low resistance means this is bright, because light will come and help the electron, give it more energy to carry the charges. So high. I like this. Alright, moving on. Here again you have an LDR and then another resistor and a battery. Resistance of the LDR is equal to the resistance of R when no light falls on the LDR. Okay. When the light intensity falling on the LDR increases, which statement is correct? Okay, so for this particular question, right, you think about it this way. Did they tell you? This question, they didn't tell you what happens to the LDR resistance with light intensity. But all LDRs will behave the same, okay? So, yeah. Anyway, when no light, so in darkness, RLDR will be equal to R. So the potential difference across them is the same. When the light falling on LDR increases, that means bright, your RLDR will decrease. Okay? So if the resistance in the LDR decrease, the current in R decreases? No. The current in LDR decreases? No. Effectively, right, current must increase. Why current increase? Because the resistance of the LDR decreases, so the total resistance of your circuit also decrease, meaning the total current that's flowing in the circuit will increase. Okay, so A and B throw away. Potential difference across R decreases, or potential difference across LDR decreases. Of course, it will be across the LDR that is decreasing, because the resistance of the LDR decrease, so the potential difference across the LDR will also decrease in proportion. Potential difference across R will increase because of ratio. Previously, let's say for example, my resistor and LDR is 1:1, half ma. How I know it's half? Because equal. Okay. Now when light is shine on me, I am LDR, my resistance begin to drop. So now instead of 1:1, maybe it's 1:2. So the external resistor will have a higher resistance. Not higher resistance, higher share, because my resistance has dropped, even though that resistance did not change. Okay, it's a matter of ratios. Okay, we'll continue, discuss this one. Okay, oh, look at this, fresh, so fresh. Okay, the resistance of the variable resistor increased. What is the effect on the reading of the ammeter and the voltmeter? Okay, so if we increase this resistance of the variable resistor, let's check about the voltmeter first lah. If the resistor beside me has an increase in resistance, it will take a larger share of the voltage. Because it took a larger share of the voltage, this resistor here will have a smaller share. Okay, so this R will increase, meaning this V will increase. Let's say this V1, R1. Okay, so if something that is in series with me has an increase in potential, my reading will decrease. Okay, so out. Alright, next. You might be tempted to say unchanged because you see it means this branch never changed also, but you wait, tomate. Number one, if you increase the resistance of this branch, the effective resistance, let's say from point A here to point B here, increases. The whole branch resistance will increase. Meaning to say, now the current, let's think about your parallel circuit. When your current reach this juncture A, or it might be thinking, I could turn now and encounter a lot of resistance, or I might choose to go ahead and encounter less resistance. Okay? Meaning, right, if you're talking about current is shared across the branches and is also in proportion to resistance, but inverse. The higher the resistance, the less current will flow into that branch, so that the potential maintain the same. V equal IR. Parallel, so V is constant, I is inversely proportional to R. Okay, V is constant, you throw it. Remember I told you ratio is best friend? So this means the current, let's say this is I1. Wait, this is I1 through the branch 1 here. Let's say we call this I1, this is I2. When the resistance between AB increases, I1 will drop to maintain the same potential of the battery. If I1 drop, this means I2 will increase. Because conservation of charge, one current decrease, the other current gets the extra lah. So the answer is B. Alright. Okay, moving on. How many questions did I put here? Hopefully not too much. Okay, in the circuit below, P has a potential meter of total resistance 10 ohm. Sure. And Q is a fixed resistor of 10 ohm. So P and Q are identical, 10, 10. I'm just going to write here. Battery is 4 volt. Voltmeter has very high resistance. So an ideal voltmeter should have infinite or very high resistance. This means there's no current flowing through the voltmeter. This means that the voltmeter will not affect the circuit. Okay? So the slider on the potential meter is moved from X to Y. So this so-called potential meter can be an entire wire, okay, or it can just be a variable resistor. Okay, so basically I can move from here to here lah. Alright, so I think we have done this question before. It's very similar to the 3 resistor question just now. Now when the voltmeter is at point Y, right, it will only measure the potential difference across Q. So the potential difference across Q, since the resistance is the same, so it will share equally 2 volt, and the whole thing here is 2 volt. So the minimum value at Y is 2 volt. So this one wrong liao lor, this one wrong liao lor, this one wrong liao lor, then you got this one. Y is 2 volt. And then when you move over to X, you cover both resistor, it would be 4 volt. And the reason why it's linear is because I'm assuming this is a uniform wire lah. Okay, so when you touch the wire, it is linear. Alright, moving on. Oh, what this? Okay, so now you have a 12 volt battery in series with the ammeter. 2 ohm resistor, 0 to 10 variable resistor. High resistance voltmeter is connected. Okay. Resistance of the variable resistor is changed from 0 to maximum. Alright, which graph shows the potential difference measured by the voltmeter and the current measured by the ammeter? Okay, let me ask you first a question. Can the current ever be 0? And the answer to that would be no. The current will never be 0. Hi. Okay, so I'm making a correction video in case you are wondering why of the abrupt change in costume. Or maybe secretly I am a musical performer, the many identities of Miss Lee. Alright, so when I say the current is never 0, this is because when you look at this, right, we can check, just check. So we start with the N range. So we're going to start when R is, let's say, the largest value, 10 ohm. The total resistance will now be 12 ohm. Okay, so your I would be 12 over 12. V equal IR ma. So 12 volt divided by 12 ohm. I would be 1 ampere. Okay, and the potential difference across this one will be 10 volt. So I think this one is 1 ampere, 10 volt. Alright, and let's check the other one. Let's say you take I is 0. So that means the only resistance left is the 2 ohm resistor divided by 2. So 12 divided by 2 will give you 6. Okay, so this value, the current here is probably 6. So you can see at this point your current is never 0. So this one current can be 0, wrong law. This one current can be 0, wrong law. So this one also maybe can, but you can see from the trend it is opposite. Okay, so from here this would be 6 ampere. And the second thing is when the voltmeter reading will be 0. Okay, because so in the first situation the voltmeter reading is 10 volt. In this situation the voltmeter reading is 0 volt, because when this is 0 ohm, there's no potential difference. It's as if this is just a wire, so there is no energy conversion. No energy conversion means no potential difference. So that's why the potential will drop back to 0. So that would be your answer, which is D. Well done, those of you who spotted the mistake. So the moral of the story is, if a teacher teaches and does too many questions, the brain also a bit taufu already at the end of the day. Alright, so thank you for correcting, making a correction if you spot it. If you have no idea what we're talking about, it's okay. This is the question. And that's it. Let's go on to the next one. Alright, moving on. Same year, different variant. Alright, let's look at a similar question. But are they really that similar? So here you have two very similar circuit. You can compare them, okay? Because it's the same year, it's just a different variant. Alright, so if you're looking at this particular circuit, right, you will notice that the only difference is I install another voltmeter across the 2 ohm. Okay, and after installing that voltmeter across the 2 ohm, I have actually a very different circuit, a different monster entirely. Okay, so let's check it out. Alright, so one thing I know about the voltmeter reading is now this one will be purely measuring the potential difference across the resistors respectively lah. Okay, the next part would be, let's think about the value, your P and Q. They cannot increase together with current at the same time, because that kind of makes no sense. Because you can see when the resistance of the variable resistor is changed from maximum value to 0. Okay, so let's say we play with the maximum values now. Okay, so let's say now we are dealing with 10 and 2 ohm. Alright, so for example, right now you know that you can see that they are sharing 12 volt. So this P would be 10 volt and the Q would be 2 volt. So P will be big and then Q will be small. Maximum value to 0. So this is my initial starting value. P would be much more bigger than Q. P is much more bigger than Q. Because maybe this, like you see, when you first start, maybe this one is 10 and maybe this one is 2. Okay, and P can drop to 0 because when this potential difference is 0, now this one will not measure the terminal voltage, because the terminal voltage, if you consider this, right, now your point A and point B, there's an interference of another voltmeter. The other voltmeter will be like, sorry, I'm already here, so you can't measure anything, because it will measure the potential difference from here to here lah. So it's going to measure potential difference from here to here. But there's nothing from here to here, because this one is 0 already. And it cannot measure the terminal potential because it's not a wire. There's another voltmeter here. So in other words, it's a slightly different kind of consideration. Okay. So yeah, that's the whole idea of it. And then you can see as this potential decreases, Q will be able to take more and more. So Q will increase as P decreases. Okay, so you got D. All right, moving on. Okay, this one is also frequently asked. When I say frequently asked, I mean students frequently ask me lah. All right, so this one, there's a power supply, potential meter, yada yada, fixed resistor. Okay, so the distance D between the slider and the sliding contact and the particular end of the potential meter is varied, so I'm changing the value of D. Current measured is then plotted against the distance D. Which two circuits will have identical graphs? Okay, so basically right now I'm going to draw a graph of my straight lines, very bad. I'm going to draw a graph of I ammeter reading against D. So basically I'm looking at how the current changes. So let's examine the circuit one by one. Let's consider this circuit. Okay, so when the current flows out from the positive terminal, it will pass through here, bypass the D length portion of the resistor before exiting through the jockey and coming like this, and then passing through the whole resistor here, and then going home lah. Okay, bye bye. Okay, now let's consider the second one. The second one will be like, I will go in here, I'll pass through again the same length that is D, and then I will be able to exit here and come here, and then I'll pass through this resistor, and then I'll go through ammeter, and then I'll return to the negative terminal. So these two are actually fairly similar lah. Fairly. Okay, let's look at the rest. Right, what about this one? This one will go like this, follow the wire, but it will not pass through the portion D. Okay, the portion that is marked by the length D is empty. Okay, because of the positioning of the jockey. So this is definitely out already, although it does pass through the external resistor, okay, or the other resistor. So Y is out. Okay, so let's consider this one. This one will pass through here. Very good, pass through the portion that is D, the D length of the variable resistor, but unfortunately it doesn't pass through the second resistor before going back. So Y and Z are not identical, W and X are identical. So your answer is A. Okay. Alright, moving on. We're almost done. Okay, and then this one, oh, time for some structure lah. Alright, paper 2. Here you have a battery of 12 volt, LDR of negligible internal resistance. You have LDR, 12 kilo ohm. And then you got the switch. Sure. Ammeter is connected in series. LDR and S are connected across point XY. Switch S is open. Calculate the potential difference across XY. Okay, so when S is open, you can assume the LDR is not there. If you want to find the potential difference across XY, this is a very nice bonus. We can use ratios, okay? XY's portion is 12. Total resistance in that branch would be 12 plus 8, and you are sharing 12 volt. Okay, so this would be 12 divided by 20, 7.2 volt. This is an older past year lah, so they are a bit more generous with marks. They are less generous these days, so maybe this would only be 2 marks. Another alternative method, if this makes you uncomfortable, is you can always use V equal to IR ma. Okay, you find the I first law. So 12 will be equal to the current and the total resistance, which is 8 plus 12 because they are in series. This is kilo ohm lah, okay? So I'm going to times 10 to the power of 3 here. So I will get I would be equal to 0.6. 12 divided by 20. Yep, 0.6 divided by 10 to the power of 3. So times 10 to the power of negative 3. ampere, milliampere. So this one is on the whole circuit. Once I know the current flowing through the circuit here, because the current will go like this, right? 0.6 milliampere. I can use V is equal to IR again, but through the 12 kilo ohm resistor. So Vxy will be 0.6 times 10 to the power of -3, and then the resistance is 12K times 10 to the power of 3. So 0.6 times 12, this would be 7.2 volt. This kind of working looks like it's worth 3 marks, right? Okay, sure. But I like ratio. See, it's the same thing, So ratio is a bit of a shorter way because you are bypassing the fact that they have the same current. You don't need to find the current. I'm just going to put the OR here. They are both fine. If your brain hang, you can always V equal to IR your way out. Alright, now we close switch S. The resistance of the LDR is 4K. Calculate the current in the ammeter. Okay, this would be the total current through the battery. So this is 4 kilo ohm. I'm going to total up the effective resistance now, okay? So this two is parallel. So, and I can just, up to you whether you want to do it together or separately. I guess just to cater to some of us who might prefer to do it slowly, I will do it slowly. But if you can do it fast, do it together in one equation. So here you have the 4 and 12 in parallel. 1/12 plus 1/4 -1 plus, so I've collapsed these two already because they're in parallel, and then the 8 kilo ohm is in series, so plus 8. I know that there is a K. Don't worry, I add that back in later because the 12, the 4 and the 8 are in kilo ohm, so I can write this one first. Okay, so you notice that for me, I tend to write power -1 because, you know, younger me forgotten to invert, then the whole question wrong, very pain, right? So I write the -1 there to remind myself to invert. So 1/12 plus 1/4 is 1/3, so this one will become 3. 1/3 inverted is 3. So you get 3 plus 8, which is 11 ohm. Alright, so once we have that, then we can now look for the, what are we looking for again? Current. Okay, V equal to IR, and again for everybody, the whole circuit. For everybody. Alright, so the potential difference of the circuit was 12. Okay, current, this is 11. Whoopsie daisy. K, so times 10 to the power of 3 ohm. So what I mean by you can do it together is you can do this RT and put it inside here. T for total. So you can find your current law, which is 12 divided by 11. That would be 1.09 milliampere. Let me check the unit first. Ampere, okay, times 10 to the power of -3 ampere. Okay. Always follow the unit that is given. If you go and put 1.09, then you lose 1 mark lah. Okay, switch S remains closed. Alright, the intensity on the LDR is increased. State and explain the change on the ammeter reading and the potential difference across XY. Okay, one by one. People don't like this kind of question. They see lines, they panic. You do not panic. You got this. Okay, so intensity of light is increased. First thing you need to mention is what happens to the resistance of the LDR. So when the intensity of the LDR, when the light intensity increases, resistance of LDR decreases. So for example, previously the LDR was 4, maybe now it becomes 2. So what happens to your total resistance? Let's say you don't know, so you press calculator. 1/12 plus 1/2 and then you invert it, you get 1.7 instead of 3. So if the resistance of the LDR decreases, this means that, okay, let's go back to the circuit a bit. This means that the resistance across XY, the effective resistance across XY will decrease. Okay? Generally, right, when two resistors are in parallel, the sum of the resistance must be smaller than any individual resistor. Mathematics, right? So let's say you take 1/2 plus 1/2 plus 1/2, the answer must be less, and invert it, the answer must be less than 2. I don't teach maths, okay, so I can prove it, but that's not the point. Okay, if not, you just put some number here that is smaller than 4, and then you calculate and see whether it's bigger than or smaller than 3 to convince yourself. Okay, so resistance of LDR decreases, and when the resistance of LDR decreases, this shows that the effective resistance across the points XY decreases as well. And because of this, the total resistance of your circuit, because it's in series, XY is in series with the 8 ohm. So total resistance of the circuit decreases too. Hey! So if everybody decrease, what will happen? Hence, current increase, and if current increases, the ammeter reading increases. Okay, I don't really know where the marks are. I can pull up the mark scheme now, but generally, right, I would suggest that you relate what happens to the LDR and what happens to the total resistance. Okay, and then the second one would be relating the current to the ammeter reading. You have to answer the question, so you need to go back to the ammeter reading. Okay, next, potential difference across XY. So you already know that the effective resistance across XY decreases. So you can say, since you already explained here, so you don't have to explain again, no? Since the effective resistance across XY decreases, the potential difference across XY decreases as well. Okay? Alright, so that's all about the potential divider. I will see you in the next video where we will talk about the potential meter. Exciting times. See you there then. Bye-bye.